Kansas City, Missouri. July 17, 1981. A Friday evening at the newly opened Hyatt Regency Hotel. The grand atrium, a marvel of modern architecture, pulsed with energy. Hundreds gathered for a lively tea dance, a weekly social event. Laughter, music, the clinking of glasses, it was an atmosphere of celebration, oblivious to the silent, unseen tension building within the very structure they stood upon. A design that promised elegance and innovation, yet harbored a fatal flaw, was about to betray its trust in the most horrifying way imaginable. At precisely 7:05 p.m., the music abruptly ceased. A piercing crack, then a thunderous roar, ripped through the atrium. The fourth-floor walkway, suspended high above the lobby, shuddered. In a horrifying cascade, it tore free from its supports, plummeting onto the second-floor walkway below. For a moment, the world seemed to hold its breath, before the combined weight of both structures, laden with dozens of people, crashed to the concrete floor. The joyous sounds of the evening were instantly replaced by screams, dust, and the chilling silence of utter devastation. The immediate aftermath was a scene of unimaginable chaos and heroism. First responders, hotel staff, and even guests scrambled through the wreckage, searching for survivors amidst twisted steel, shattered glass, and broken concrete. The scale of the tragedy quickly became apparent. What began as an evening of innocent revelry had transformed into a mass casualty event, etched forever into the city's memory. This was not merely an accident, it was a structural failure of profound magnitude, questioning the very foundations of modern engineering and design. By the time the dust settled and the rescue operations concluded, the true horror of the collapse was undeniable. 114 people had lost their lives, and over 200 were injured, many permanently. It remains one of the deadliest structural failures in American history, a stark reminder of the immense responsibility borne by engineers, architects, and builders. This wasn't a natural disaster, it was a catastrophe born from human design, a flaw that would unravel under intense scrutiny, exposing systemic issues in the engineering profession. How could such a catastrophe occur in a modern, seemingly robust structure? The question haunted a nation. For engineers and the public alike, understanding the why became paramount. The investigation would reveal not a dramatic structural collapse in the traditional sense, but a subtle yet catastrophic design modification, a change that seemed minor on paper, yet fundamentally altered the load paths and stress distribution within the walkway's suspension system. This was the smoking gun, a seemingly innocuous alteration that sealed the fate of over 100 innocent lives. To understand the failure, we must first appreciate the original vision for the Hyatt Regency Kansas City. Completed in 1980, its signature feature was a vast, multi-story atrium, an architectural statement designed to impress. Spanning the atrium were 3 suspended walkways, connecting different wings of the hotel. These elegant structures were intended to be a dynamic part of the guest experience, offering panoramic views of the bustling space below. Their design was integral to the hotel's modern aesthetic, a symbol of its ambition and contemporary flair. The walkways were not supported from beneath, but dramatically hung from the ceiling structure above, creating an illusion of lightness. This suspension was achieved using long, threaded steel rods, often called tie rods or hanger rods, which passed down through the walkway's steel box beams. These box beams formed the primary structural element of the walkways, providing their strength and rigidity. The concept was innovative, aesthetically pleasing, and, in theory, structurally sound. The key was in the connection, how these rods met the beams. In the initial design drawings, the intent was clear: a continuous tie rod would extend from the atrium ceiling, passing through the fourth floor box beam, and then continue downwards to support the second floor box beam. At each walkway level, a large nut would be threaded onto the rod, resting against a washer plate at the underside of the box beam. This single rod system was elegant, distributing the combined weight of both walkways, plus their occupants, directly up to the ceiling support. It was a straightforward and robust design, or so it seemed. However, constructing this original design presented a practical challenge. Fabricating and erecting one exceptionally long, continuous tie rod that accurately passed through two separate box beams, aligning precisely, was difficult. It required extreme precision in manufacturing and assembly, along with careful coordination on site. This logistical hurdle, common in complex construction projects, often leads to field modifications. And it was here, in the pursuit of ease and efficiency, that the seeds of disaster were sown, subtly changing the fundamental mechanics of the structure. To simplify construction, a critical design change was introduced by the steel fabricator and subsequently approved by the project's structural engineers. Instead of a single continuous tie rod, two separate, shorter rods were used for each suspension point. One rod extended from the ceiling down to support the fourth-floor walkway. A second, independent rod then hung from the underside of the fourth-floor box beam, supporting the second-floor walkway. This seemingly minor alteration eliminated the need for a single, impossibly long rod. On the surface, this two-rod system might appear functionally equivalent. However, its impact on the structural integrity was profound. In the original design, the fourth-floor box beam merely transferred the load from the second-floor walkway around its own connection point. With the modification, the fourth-floor box beam was now directly supporting the entire weight of the second-floor walkway, in addition to its own. The load path was fundamentally altered, creating a critical point of stress where none had been intended. Let's zoom in on the specific connection point at the fourth-floor walkway. In the modified design, the lower tie rod, supporting the second-floor walkway, was no longer merely passing through the fourth-floor box beam. Instead, it was threaded into a nut that rested directly on a washer plate, which in turn sat on the underside of the fourth-floor box beam. This meant the box beam itself was now responsible for bearing the direct load of the walkway below, transmitted through this single connection point. Crucially, the original design had the load from the second-floor walkway bypassing the fourth-floor box beam, simply transferring it upwards. The modification effectively doubled the load on the connection at the fourth-floor box beam. The nuts holding the lower rods now had to support the full weight of the second-floor walkway, while simultaneously, the nuts holding the upper rods had to support the combined weight of both the fourth-floor walkway and the now hanging second-floor walkway. This was a monumental increase in stress at a critical juncture. The strength of this connection depended entirely on the capacity of the steel box beam and the small area around the nuts. The nuts themselves were designed to carry significant tension along the tie rod. However, when these nuts were threaded onto the upper section of the lower tie rod and held in place below the fourth-floor box beam, the entire force from the lower walkway was transmitted through this small connection. This force was far greater than the original design intended for that specific point, creating a punching shear scenario. Compounding the problem, the fourth-floor box beam was constructed from two steel channels welded together. The nuts holding the lower tie rods were designed to bear against the bottom flange of this box beam. However, the connection between the flange and the vertical web of the channel was a simple fillet weld. This weld was adequate for the original design, where the beam itself wasn't carrying the direct vertical load of a lower walkway. But under the modified design, this weld was placed under immense, direct tension and shear forces it was never designed to withstand. As more people gathered on the walkways that fateful evening, the load incrementally increased. The connections, already critically overstressed by the design modification, approached their ultimate limit. The fourth-floor walkway, carrying not only its own weight and occupants but also the entire weight of the second-floor walkway and its occupants, reached a tipping point. The structural capacity of the critical weld and the steel around the nuts was simply insufficient to resist the immense tensile forces. Imagine the threaded nut, gripping the steel rod, trying to pull through the thin flange of the box beam. The metal around the nut, weakened by the inadequately welded connection, began to deform and tear. Once one connection failed, the entire load instantly redistributed to the remaining connections, overloading them in turn. This cascading effect led to rapid, catastrophic failure across all support points for the fourth-floor walkway. It wasn't a slow sag, it was a sudden, violent ripping apart of metal under unbearable tension. The fourth-floor walkway, having lost its primary support, plunged downwards. Its descent was not halted, but instead, it impacted the second-floor walkway directly below. The force of this impact, combined with the additional weight of the collapsed structure, was overwhelming. The already heavily loaded support system for the second-floor walkway could not withstand this sudden, compounded dynamic load. In a terrible, almost simultaneous sequence, both walkways collapsed onto the ground floor, carrying with them scores of unsuspecting individuals. The critical question remains, how could this fundamental design flaw, this fatal modification, go unnoticed and uncorrected? The change itself wasn't inherently complex, but its implications for structural mechanics were profound. The tragedy exposed a severe breakdown in communication and accountability between the structural engineers responsible for the overall design and the steel fabricators who proposed the easier construction method. It highlighted a dangerous blind spot in the professional review process, a failure to scrutinize what appeared to be minor adjustments. In the immediate aftermath of the collapse, the scene was one of overwhelming destruction. Emergency services were quickly overwhelmed, but the response from the community was immense. Doctors, nurses, and ordinary citizens converged on the hotel, forming human chains to help move debris and aid the injured. The focus was on rescue and recovery, sifting through the tangled mess of steel, concrete, and personal belongings. Amidst the heroism, a somber realization began to dawn: this was a disaster that demanded a thorough, uncompromising investigation. The primary agencies to lead the investigation were the National Bureau of Standards, now NIST, and the National Transportation Safety Board, NTSB, along with state and local authorities. Forensic engineers, specialists in analyzing structural failures, immediately descended upon the site. Their task was monumental: meticulously examine every piece of fractured metal, every bent beam, every twisted rod, to reconstruct the sequence of events that led to the collapse. They worked methodically, collecting evidence that would piece together the engineering narrative of the tragedy. Central to the investigation was the reconstruction of the walkway's original and modified designs. Investigators pored over blueprints, architectural drawings, and fabrication shop drawings. They discovered the stark difference between the initial design, which specified continuous hanger rods, and an as-built modification. This discrepancy immediately raised red flags. The focus narrowed to the connection points at the fourth-floor walkway, where the critical failure was suspected to have originated. Through extensive material testing and structural analysis, the investigators confirmed their suspicions. The fillet welds connecting the bottom flange of the fourth-floor box beam to its vertical web were indeed the primary failure point. Under the significantly increased load of the modified design, these welds had simply ripped apart, unable to bear the immense tension. This failure then initiated the complete collapse, as the box beam could no longer effectively support the lower tie rod. With the technical cause identified, the investigation moved to pinpoint responsibility. It centered on the structural engineering firm, Jack D. Gillum and Associates, and the steel fabricator, Havens Steel Company. The fabricator had proposed the design change, citing ease of construction. Crucially, the structural engineers, despite reviewing and approving the modification, failed to adequately analyze the profound impact it would have on the load-bearing capacity of the critical connections. This oversight was deemed a fundamental breach of their professional duty. The investigation concluded that the structural engineers were grossly negligent. Their approval of the modified design without proper review constituted professional misconduct. They had a professional and ethical obligation to ensure the safety and structural integrity of the building, an obligation they failed to uphold. This wasn't merely a clerical error, it was a fundamental oversight in professional judgment that led directly to a catastrophic loss of life. The findings sent shockwaves through the engineering community, forcing a painful examination of self-regulation and professional standards. Beyond the technical findings and legal repercussions, the human cost of the Hyatt Regency collapse was immeasurable. Families were shattered, lives forever altered. Survivors grappled with physical disabilities and deep psychological trauma. The tragedy served as a brutal, visceral reminder that engineering is not merely about calculations and blueprints, it is about protecting human lives. Every rivet, every weld, every structural decision carries the weight of potential consequence, a burden that demands the utmost diligence and ethical integrity. The Hyatt Regency collapse became a watershed moment in engineering ethics. It forced a paradigm shift within the profession, moving beyond mere technical competence to emphasize ethical responsibility and accountability. Engineers could no longer simply pass the buck or assume that a design modification proposed by another party would automatically be structurally sound. The disaster underscored the paramount importance of independent review and thorough verification at every stage of a project, from initial concept to final construction. In response to the tragedy, building codes and engineering standards were rigorously reviewed and significantly strengthened across the United States. New requirements were implemented, particularly regarding the review and approval of design changes, mandating that such modifications receive the same level of scrutiny as the original design. The disaster prompted a greater emphasis on detailing connections and ensuring that the entire load path within a structure is clearly understood and verified by a licensed professional engineer. The collapse highlighted the critical necessity of independent peer review, especially for complex or innovative designs. While not always mandated, the practice of having an independent engineering firm review critical design elements became much more prevalent. This added layer of scrutiny aims to catch potential errors, misunderstandings, or overlooked details before they become catastrophic realities. It reinforces the idea that no single engineer or firm is infallible, and multiple eyes can often prevent disastrous oversights. The individuals directly involved in the design and approval of the flawed modification faced severe professional consequences. The licenses of the responsible engineers were revoked or suspended, a stark warning to the profession. This unprecedented level of accountability solidified the principle that engineers are personally and professionally liable for their work. It underscored that engineering is not just a technical craft, but a licensed profession with profound legal and ethical obligations to public safety. One of the most significant lessons learned from the Hyatt Regency disaster was the critical importance of clear, unambiguous communication throughout the design and construction process. Any proposed change, no matter how minor it appears, must be thoroughly documented, communicated to all relevant parties, and subjected to a comprehensive structural analysis by a qualified engineer. Assumptions and verbal approvals proved to be deadly. Precise, written communication became an enforced standard to prevent similar misunderstandings. The concept of as-built drawings also gained renewed significance. These are final drawings that reflect all changes made during construction, providing an accurate record of the structure as it was actually built. The Hyatt Regency collapse underscored the danger of discrepancies between design drawings and the finished product. Maintaining accurate and up-to-date documentation is not merely bureaucratic, it is a vital safety measure, ensuring that future inspections or modifications are based on the true structural reality. For engineers, the Hyatt Regency collapse reinforced the need for continuous professional development and education. The field of structural engineering is constantly evolving, with new materials, techniques, and analytical tools emerging. Staying abreast of best practices, understanding potential failure modes, and rigorously applying ethical principles are ongoing responsibilities. The disaster served as a powerful case study, taught in engineering schools worldwide, ensuring that future generations of engineers learn from the mistakes of the past. Ultimately, the legacy of the Hyatt Regency Walkway collapse is an ethical one. It stands as a stark reminder that the primary duty of an engineer is to protect the public's safety and welfare. This duty transcends commercial pressures, project deadlines, and minor design conveniences. It demands unwavering vigilance, integrity, and a profound understanding that every decision carries the potential for life or death. The collapse compels every engineer to ask, have I done everything within my power to ensure this structure is safe? Engineers are granted a sacred trust by society, the authority to design and construct the built environment that profoundly impacts human lives. With this authority comes immense responsibility. The Hyatt Regency disaster profoundly changed how engineers perceived their role, pushing the profession towards a culture of greater transparency, stricter accountability, and a perpetual dedication to safety above all else. It is a lesson etched in steel and concrete, remembered in the solemn silence of a reconstructed atrium. The story of the Hyatt Regency collapse is a complex narrative, not just of structural mechanics, but of human factors, communication failures, and ethical lapses. It teaches us that engineering excellence extends beyond mere calculations to encompass a holistic understanding of risk, responsibility, and the profound impact of every decision. It's a testament to the fact that even seemingly minor changes, when misunderstood or inadequately reviewed, can have the most catastrophic consequences. Decades later, the physical wounds of the Hyatt Regency collapse have healed, and the hotel has been renovated, its atrium now devoid of suspended walkways. But the memory of that July evening remains a haunting shadow over the engineering profession. It serves as an enduring cautionary tale, a permanent fixture in the curriculum of aspiring engineers, reminding them that their craft is not just about building structures, but about safeguarding lives, and that vigilance is the ultimate cornerstone of their profession. In an era of increasingly complex and ambitious architectural designs, the lessons from Kansas City are more relevant than ever. The drive for innovation must always be tempered by rigorous adherence to safety standards, meticulous design review, and an unshakable commitment to ethical practice. The tragedy underscores that every component, every connection, no matter how small, plays a vital role in the overall integrity of a structure. It is a constant call to professional excellence and a profound respect for the potential impact of engineering on human existence. The 114 lives lost on that summer night in 1981 were not in vain. Their sacrifice forged a path towards a safer future, catalyzing fundamental changes in engineering practice, ethics, and accountability. It taught us that the pursuit of innovation must always be balanced by an unwavering commitment to safety. For every engineer, the Hyatt Regency collapse is a solemn vow, whispered in the blueprints and hummed in the steel. Never again will a design flaw, preventable by diligence and ethics, claim so many innocent lives.